Our next speaker is Immanuel Kunz. He's a PhD student at Fraunhofer AISEC, and you're going to talk to us about understanding some privacy properties of programs using static data flows and analysis. So great.
Thank you. Yeah, so this presentation is about a tool called Privacy Property Graph, which has the purpose of automating privacy threat modeling using static analysis, so using a graph-based static analysis approach. And this is a joint work with Konrad Weiss, Christian Banse, and Angelika Schneider. So the obvious motivation for this is that privacy threat modeling and threat modeling in general should be done frequently. You really want to do it frequently to stay on top of finding potential threats in a design and in your application. So think of your typical agile development process, maybe where you have sprints and requirements change, you change the application often, modifications are done, etc. New features are added, and the application is potentially very large. No one really knows all the data flows in there and knows about all the threats. So it's a lot of work to go through all of this and through all the potential privacy threats regarding linkability, identifiability, non-repudiation, etc. To go through this. So we want some level of automation in there. And what I want to start with now is some background on code property graphs, which is the technical basis for this tool. Code property graphs essentially combine different types of graphs. So they're static analysis tools that really just work on the structural information of source code and build an abstraction of that in the form of a graph. And that would typically combine an abstract syntax tree, so very low-level properties of the code, like variables and functions and so on. The evaluation order, so the order in which these entities are evaluated, and most importantly for privacy analysis, the data flow graph, which shows you how these entities basically move around in the code and where they are used. So this is very helpful for privacy threat modeling because this essentially already builds a data flow diagram, which is usually the first step in privacy threat modeling. So you want this abstract representation of your design, of your system, that shows you which processes exist and storages and which data flows exist between them. So you can derive something about potential threats in there. And what we have shown in a previous work, that's called the cloud property graph actually, is that we can use this code property graph and extend it with arbitrary other information that are useful for an analysis for security of, in this case, of cloud-based systems. So what you can see here is just a very small excerpt of such a graph that shows an application there. There's a front end. There's an HTTP post request that's part of this application. It has this DFG edge here. That's a data flow graph edge. So that shows you that there's data flowing to an endpoint in this case. And when you follow around the graph a little more, you can maybe see that data is eventually stored in a database. So this is one part of the background of this work. Another part is Lintern. This is a privacy threat modeling framework that defines, I believe, 34 concrete privacy threats. So this is just one example, linkability of stored data. So this is organized in these kind of cards that will help development teams and analysts to look for privacy threats in their designs. It's just a very high-level description. In this case, personal data being stored are linkable. So you can then look into your data flow diagram to see if there's potentially, for example, different sources of data, pseudo-identifiers that are stored in the same database and are therefore linkable. That would be one example. And what we did in this work is to take all these cards, all these privacy threat descriptions, and think about what they would mean if you would want to find these in source code or in this graph abstraction. So we tried to translate the Linton privacy threats to code properties. And I'll stay kind of with this example. Personal data being stored are linkable. I cannot cover all of this now in the presentation, but just give you a few examples. So part of this threat, if you would want to detect that in the graph, would be obviously to detect pseudo-identifiers. So you want to detect the code entities that really hold this personal data. You want to detect data flows of them. You want to also detect data flows between applications to see where they flow from the user's front end, for example, to the back end. And eventually, you will also want to see in the graph where the data is stored, where there are database operations, where there are databases. So that's what we did in the first step. We translated these threads to code properties we later want to find in the graph to be able to detect them automatically. And so the next question is, we have now these properties. How do we actually get them into the graph, right? So we are using an existing library to build the basic code property graph with variables and functions, etc., and build an application on top of that that will analyze these and add the additional properties that we need in the graph to detect privacy threats. So that's what we want to have, right? That's the kind of graph we want to have later to do automatic analyses on this graph. So what you see here is, again, a very simple example of some entities you would find in a CPG, in a code property graph. There are function declarations, call expressions, member expressions. So this is the level you get when building this kind of graph. And in our implementation, we have a bunch of what we call passes. And these passes will analyze these nodes for different programming languages and different libraries in this case. So we covered a bunch of programming languages. We have focused a bit on Go and Python in this implementation, but the basic CPG we use also covers more programming languages like Java and C and others. So these passes will analyze the graph and check for the properties we are interested in. The GORM library, for example, is a database interaction library for Go that will allow you to interact with a Postgres database, for example. And once it has found the nodes that represent these database operations, it can then add these nodes to the privacy property graph. So we get these the properties we are really interested in into the graph. And what we can do now is actually analyze this graph automatically. What we are using is Neo4j. That's a graph database, and it also comes with its own query language. That's just an SQL-like query language that allows you to find interesting paths in this graph. So this is an example that would give you all the paths in the graph that start with a pseudo identifier that moves via an arbitrary number of data flow edges to an HTTP endpoint. So maybe this is not yet a privacy problem per se, right? But could be a potential threat, and we can of course specify that more precisely, and we can, for example, ask for a path of all paths of pseudo identifiers that move via data flow edges to an HTTP endpoint and are later stored in a database to find these potentially linkable storage threads that we started off with earlier. So what you can see here already is that these queries are very generic. So that's the goal of the whole implementation, that you can use these queries across applications, across programming languages, and they don't have to be adapted or changed. To evaluate the approach, we have, since there is no existing benchmark for this or an existing application, we can compare to, we have developed our own testing suite that is composed of the test cases for Go and Python, and these test cases, these are really minimal code snippets basically that that represent client-server interactions and represent these different kinds of linting threats, including linkability threats, identifiability threats, non-repudiation threats, and so on, and also non-compliance threats regarding data protection requirements. Just as a quick overview, they cover 22 out of the 34 linting threats of this framework. Using this with our tool results in 20 correctly detected threats, 11 false positives and 2 false negatives. So in conclusion, privacy threat modeling is important and is important to do frequently to catch threats early and prevent problems later on. But it's tedious work. And what we did was first use the linting privacy threat modeling framework to translate these into code properties, bring them into a code property graph, and write queries that allow you to automatically analyze this graph for potential threats. In future work, there are still some threats that were out of scope of this work, for example, also side channel threats and other types of threats that we want to address. We also want to extend the coverage of the technologies, database technologies, for example, languages and frameworks, apply the test suite with other tools and improve the usability so it can, for example, be integrated in a CI/CD pipeline. And yeah, in conclusion, this we think is pretty useful for especially large application and regression tests. So thank you for the attention.
Thanks, Immanuel. One question is, what if the DFDs are developed with errors? Would this impact the threat modeling results, or is there a way for DFDs to be verified for accuracy?
So if there are errors in the implementation of the code property graph?
I think so, yeah.
That's right. So we really rely on a correct implementation of this underlying library that we are using. Yeah. Okay. That's a limitation, yeah, right.
And another question is, what programming languages are compatible, or what language facilities are compatible with a property graph? In principle, could it be implemented for many different languages, or are there certain annotations you need, or information from the language you need?
It can be basically used for many languages, and the CPG library we are using covers C, Java, and has more experimental support, but it has support for Python, Go, TypeScript as well. So yeah, this and really abstracts all this to the same kind of graph.
Okay. And could you speak a little bit about query efficiency? You mentioned there were a few queries that you were able to execute. Are these graphs very large and these queries are expensive to execute, or relatively efficient to compute these types of data flow properties?
I don't have the numbers in my head now, but they are. It's not very expensive to run, and especially in the scenario we are envisioning this being used. Just in a threat modeling session after your development sprint, there's not a big time constraint there. So
great. Okay, great. Let's thank Immanuel again.